Welcome to a journey through the biggest threats to our Milky Way galaxy. Over the next 2 hours, we'll explore the cosmic dangers that could reshape, damage, or even destroy our galactic home. Whether you're here to fall asleep, to study, or simply to relax while learning about the universe, sit back, take a deep breath, and let the wonders and perils of our galaxy unfold before you. The Milky Way seems eternal and unchanging, but across cosmic time, many forces threaten its structure. Galaxy collisions, supermassive black holes, dark matter interactions, cosmic radiation. These threats operate on timescales of millions and billions of years, but they are real and inevitable. Let's begin our gentle journey through the biggest threats to the Milky Way. The single greatest threat to the Milky Way is not a distant danger. It is already approaching. The Andromeda galaxy, our nearest large galactic neighbour, is on a collision course with the Milky Way. Andromeda lies approximately 2.5 million light-years away. It is slightly larger than the Milky Way, containing perhaps 1 trillion stars compared to our 400 billion. And it is moving toward us at about 110 kilometers per second. This approach is inevitable, despite the expansion of the universe, which pushes distant galaxies away from us. Andromeda is close enough that gravity dominates. The mutual gravitational attraction between our two galaxies is pulling us together. Current observations and computer simulations predict that the collision will occur in approximately 4 billion years. This might seem like an incomprehensibly long time, but in cosmic terms, it is merely a few galactic rotations away. The collision will not be instantaneous. It will unfold over hundreds of millions of years. The first encounter will happen when the outer halos of the two galaxies begin to interact, their dark matter halos merging first. As the galaxies approach, their gravitational fields will begin to distort each other. The Milky Way's disk may begin to warp more dramatically. Tidal forces will pull at the outer regions, stretching them toward Andromeda. When the visible disks finally meet, the scene will be spectacular. From a planet in the Milky Way, if any civilization still exist, the night sky will be dominated by Andromeda, growing larger each year until it fills half the sky. Individual stars will rarely collide. The distances between stars are so vast that even during a galactic collision, stars pass through each other like ghosts passing through walls, but their orbits will be drastically altered by the changing gravitational field. Gas clouds, however, will collide. When dense molecular clouds from the two galaxies slam into each other, they will be compressed. This compression will trigger massive bursts of star formation, lighting up both galaxies with brilliant blue light from millions of newly born hot stars. The disks will pass through each other on the first encounter. Then gravity will pull them back together for a second pass, and perhaps a third. With each pass, the galaxies will lose energy through a process called dynamical friction, bringing them closer together. Eventually, after several close encounters over 500 million years, the two galaxies will merge completely. Their supermassive black holes will spiral toward each other, eventually merging in a cataclysmic event that will send gravitational waves rippling across the universe. The final product will be a single, larger galaxy. It'll likely be an elliptical galaxy, having lost the beautiful spiral structure of both original galaxies. This new galaxy is sometimes called Milkomeda or Milkdromeda. Our solar system, if it still exists, will likely survive the merger. The Sun will be an old red giant by then, perhaps having already consumed the inner planets, but the solar system will be flung into a new orbit, possibly far from the centre of the merged galaxy. The Andromeda collision represents a complete restructuring of our galactic home. The Milky Way as we know it will cease to exist, transformed into something entirely new. This is the ultimate threat to our galaxy's identity. The Andromeda collision is not the only galactic threat. The Triangulum galaxy, also known as Messier 33, is the third largest member of our local group, and it too may play a role in the future destruction of the Milky Way's structure. Triangulum is smaller than both the Milky Way and Andromeda, containing perhaps 40 billion stars. It lies about 3 million light-years from us, slightly farther than Andromeda. The orbit of Triangulum is complex. It may be gravitationally bound to Andromeda, orbiting the larger galaxy, or it may be on an independent trajectory through the local group. Current measurements of its motion are uncertain. Some simulations suggest that Triangulum will collide with the Milky Way before Andromeda does, perhaps 3 billion years from now. Other simulations show Triangulum colliding with Andromeda first, then the combined system later impacting the Milky Way. A third possibility is that Triangulum will be disrupted by tidal forces during the Milky Way-Andromeda merger, its stars scattered throughout the newly forming elliptical galaxy. Regardless of the exact scenario, Triangulum represents an additional source of gravitational chaos during the merger epoch. Its presence adds unpredictability to the future evolution of the local group. If Triangulum does collide with the Milky Way separately, the interaction will be less dramatic than the Andromeda collision, simply because Triangulum is smaller, but it would still trigger bursts of star formation and disturb stellar orbits throughout the Milky Way. The combined threat of both Andromeda and Triangulum means that the Milky Way faces not one, but potentially two major collisions over the next few billion years. Our galaxy exists in a cosmic shooting gallery. These interactions are not unusual in the universe. Galaxy mergers are common. Large galaxies grow by consuming smaller ones. The Milky Way itself has consumed dozens of dwarf galaxies over its lifetime, but the scale of the Andromeda-Triangulum interactions will be unprecedented in the Milky Way's recent history. The last major merger that shaped our galaxy occurred over 10 billion years ago in the early universe. The threat from Triangulum reminds us that the local group is not a stable, quiet place. It is a dynamically evolving system, with galaxies on complex orbits, gravitationally interacting, slowly spiraling toward eventual merger. The night sky of the far future will be very different from today. Instead of the faint smudges of Andromeda and Triangulum visible to patient observers, future astronomers will see enormous galactic structures dominating the heavens, growing larger with each passing million years. While Andromeda and Triangulum represent distant future threats, the Milky Way faces ongoing smaller-scale impacts from dwarf galaxies. These smaller collisions are happening right now, slowly altering the structure of our galaxy. The Milky Way is surrounded by dozens of dwarf satellite galaxies. The largest include the Large Magellanic Cloud, the Small Magellanic Cloud, and the Sagittarius Dwarf Elliptical Galaxy. Each of these is being slowly torn apart by the Milky Way's tidal forces. The Sagittarius Dwarf Galaxy is currently passing through the Milky Way's disk. Its stars are being stripped away, forming long tidal streams that wrap around our galaxy multiple times. This disruption is adding mass to the Milky Way but also disturbing the disk. Each time a dwarf galaxy passes through or near the Milky Way's disk, it creates gravitational ripples. These ripples can perturb the orbits of stars in the disk, potentially scattering them into higher orbits or even ejecting some stars entirely. The Large Magellanic Cloud is particularly concerning. It is the most massive of the Milky Way's satellites, containing perhaps 30 billion stars. Recent measurements suggest it may be on a collision course with the Milky Way, potentially impacting us in about 2.5 billion years. If the Large Magellanic Cloud does collide with the Milky Way, the impact could be significant. Though much smaller than Andromeda, the LMC is still massive enough to disturb the Milky Way structure, possibly triggering the growth of the central bar or altering the spiral arm pattern. Computer simulations show that the LMC collision could even wake up the supermassive black hole at the Milky Way center. The influx of gas from the LMC might feed the black hole, causing it to become an active galactic nucleus for a period of time. An active galactic nucleus would pose its own threat. The central black hole would emit powerful radiation and launch jets of material outward. This could heat the gas in the inner galaxy, potentially suppressing star formation for millions of years. Dwarf galaxy disruptions also inject energy into the galactic halo. The kinetic energy of the infalling satellite is transferred to the halo stars through gravitational interactions, heating the halo and potentially expanding it. Over cosmic time, the cumulative effect of many dwarf galaxy mergers has shaped the Milky Way's halo. The halo is not a smooth structure, but a complex mix of stellar streams, each representing a past merger event. These ongoing disruptions mean the Milky Way is constantly under attack from smaller systems. While each individual dwarf galaxy poses only a minor threat, the collective effect over billions of years is significant. The Milky Way grows through these mergers, but growth comes at a cost. Each merger adds complexity and disorder to the galactic structure. The disk becomes more turbulent. The halo becomes more chaotic. The ordered beauty of the spiral galaxy is gradually eroded. At the very center of the Milky Way lurks a supermassive black hole. Sagittarius A star, as it is called, contains over 4 million times the mass of the Sun compressed into a region smaller than Mercury's orbit. This monster poses a constant, if subtle, threat to the galaxy. Currently, Sagittarius A star is relatively quiet. It is not actively consuming large amounts of material. The black hole is essentially dormant, accreting gas at a very low rate. But this quiescence may not last forever. If a large cloud of gas were to fall toward the black hole, it would be captured by the intense gravity. The gas would form an accretion disk, spiraling inward while heating to millions of degrees. As it falls, the gas would emit enormous amounts of radiation. This radiation could affect the entire inner galaxy. High-energy X-rays and gamma rays from the accretion disk would ionize gas throughout the central region. Powerful winds driven by the radiation could blow gas out of the galactic center, suppressing star formation. We know such events have happened in the past. The Fermi bubbles, two enormous lobes of gamma-ray emission extending above and below the galactic plane, are thought to be remnants of a burst of activity from Sagittarius A star a few million years ago. During that event, the black hole must have consumed a substantial amount of material, perhaps thousands of solar masses of gas or even an entire star cluster. The energy released carved out cavities in the galactic halo and launched material to distances of tens of thousands of light years. If such an event were to happen again, the consequences for the inner galaxy would be severe. Star-forming regions near the galactic center could be disrupted. The intense radiation could strip away the atmospheres of planets in the central regions, sterilizing any worlds that might harbor life. The black hole also poses a direct threat to stars that venture too close. Stars in the central star cluster orbit very near the black hole. If a star's orbit takes it close enough, tidal forces can tear the star apart in what astronomers call a tidal disruption event. During a tidal disruption event, half of the star's material is typically captured by the black hole, while the other half is ejected at high speed. The captured material forms a bright accretion disk that can outshine the entire galaxy for weeks or months. Such events are rare but inevitable. Every few tens of thousands of years, a star in the central cluster will wander too close to Sagittarius A star and be destroyed. Each event represents a violent threat to any planetary systems around the doomed star. The black hole also influences stellar orbits throughout the central region. Stars near the black hole move at tremendous speeds, some reaching several % of the speed of light. These high-speed stars experience significant time dilation and gravitational redshift. If two stars on highly elliptical orbits around the black hole were to collide, the energy released would be enormous. Such collisions may be rare, but over billions of years they are likely to occur, adding to the violence of the galactic center. The supermassive black hole represents a permanent threat at the heart of the Milky Way. It is a gravitational trap from which nothing can escape once captured. It is a potential source of devastating radiation, and it is slowly growing, consuming any material that ventures too close, becoming more massive and more dangerous with each passing million years. Throughout the Milky Way, there are stars moving at extraordinary speeds, fast enough to escape the galaxy entirely. These hypervelocity stars represent both a curiosity and a threat, their origins tied to the most violent processes in the galaxy. Hypervelocity stars travel at speeds exceeding 600 kilometers per second, far faster than the typical orbital velocity in the galactic disk. At these speeds, stars can escape the Milky Way's gravity and journey out into intergalactic space. Most hypervelocity stars are thought to originate from the galactic center, a binary star system orbiting too close to Sagittarius A star can be disrupted by the black hole's gravity. One star is captured while the other is flung outward at tremendous speed, becoming a hypervelocity star. These ejected stars travel through the galaxy like cosmic bullets. Though space is vast and collisions are unlikely, the sheer speed of these stars means that any encounter with a gas cloud, star cluster, or planetary system could be catastrophic. A hypervelocity star passing through a molecular cloud at 600 kilometers per second would create a powerful shockwave. This shock could compress the cloud, potentially triggering star formation, or it could disrupt the cloud entirely, preventing stars from forming. If a hypervelocity star were to pass close to a populated star system, the gravitational effects could be significant. Though a direct hit is virtually impossible, a close passage could perturb the orbits of planets, especially outer planets and comets in the system's distant reaches. The Oort cloud surrounding our own solar system is particularly vulnerable to such perturbations. A close passage by a fast-moving star could send thousands of comets plunging toward the inner solar system, creating a prolonged period of heavy bombardment. Hypervelocity stars also carry material with them as they travel. Any planets or debris disks around these stars are subjected to extreme conditions. The interstellar medium, normally very diffuse, becomes a dense obstacle when encountered at such high speeds. This creates intense friction and heating. Atmospheres of planets around hypervelocity stars would be stripped away by the ram pressure of the interstellar medium. Any life on such worlds would face an existential threat from the extreme environment. From the Milky Way's perspective, hypervelocity stars represent a slow leak of mass. Each ejected star removes matter from the galaxy, never to return. Over billions of years, this gradual loss could become significant. Estimates suggest that hundreds of hypervelocity stars may be launched from the galactic center every million years. While each individual star is tiny compared to the galaxy's total mass, the cumulative loss over the Milky Way's lifetime is measurable. These stars also carry metals, elements heavier than hydrogen and helium, out of the galaxy. This represents a loss of enriched material that could otherwise be incorporated into new generations of stars and planets. Hypervelocity stars remind us that the Milky Way is not a closed system. Matter can escape. Stars can be ejected. The galaxy is slowly losing mass to intergalactic space, and this process has been ongoing since the galaxy formed. The threat posed by individual hypervelocity stars to any specific region of the galaxy is minimal, but their existence highlights the violent processes operating at the galactic center and the constant, if gradual, erosion of the galaxy's mass. Among the most violent events in the galaxy are supernova explosions. These stellar deaths release more energy in a few seconds than the Sun will emit in its entire 10 billion year lifetime, and they pose a significant threat to nearby regions of the galaxy. Supernovae occur when massive stars reach the end of their lives. Stars more than 8 times the mass of the Sun eventually exhaust their nuclear fuel. When this happens, their cores collapse catastrophically, triggering an explosion that blows the star apart. The explosion releases a burst of high-energy radiation, including X-rays and gamma rays. This radiation can be lethal to life on nearby planets. If a supernova were to occur within a few dozen light-years of Earth, the radiation dose could be enough to damage the ozone layer, exposing the surface to deadly solar ultraviolet light. But the radiation burst is just the beginning. The supernova also launches a shockwave of material into space. This ejector, travelling at thousands of kilometers per second, crashes into the surrounding interstellar medium, creating a supernova remnant. The shockwave can extend for tens of light years. As it expands, it compresses and heats the gas it encounters. This compression can trigger the collapse of nearby molecular clouds, leading to new star formation. In this way, supernovae create the seeds of their stellar descendants. But the shockwave is also destructive. Any star system in the path of an expanding supernova remnant will be subjected to intense pressure and heating. Planetary atmospheres can be stripped away. Cometary orbits can be disrupted. Life, if it exists, will struggle to survive. Supernovae are also the primary source of cosmic rays in the galaxy. These high-energy particles are accelerated by the shock fronts of supernova remnants. Once launched, cosmic rays stream through the galaxy, ionizing gas and potentially damaging biological molecules. High cosmic ray fluxes near supernova remnants pose a threat to space travelers and to any advanced civilizations attempting interstellar travel. The radiation environment near a recent supernova is hostile and dangerous. In the Milky Way, supernovae occur at a rate of roughly 1 to 3 per century. Most happen far from the solar system, in distant spiral arms, or in the crowded central regions. But occasionally a supernova will occur nearby. The last nearby supernova was in 1604, observed by Johannes Kepler. Before that, Tycho Brahe observed one in 1572. Both were visible to the naked eye and occurred several thousand light years away. If either had been 10 times closer, the effects on Earth could have been significant. Looking forward, astronomers monitor massive stars in our cosmic neighbourhood. Betelgeuse, a red supergiant in the constellation Orion, is a candidate for a future supernova. At about 600 light-years away, its explosion would be spectacular but not dangerous. Other stars, closer and more massive, could pose greater threats. But predicting exactly when a star will explode is difficult. Massive stars are unstable in their final stages, and the collapse can be triggered suddenly. The cumulative effect of many supernovae over the history of the galaxy has been profound. They have enriched the interstellar medium with heavy elements. They have carved out vast bubbles and cavities in the gas. They have driven the galactic fountain and shaped the structure of the disk. But each supernova is also a localized catastrophe. For any life, any planet, any star system within the danger zone, a supernova is an existential threat, a cosmic disaster from which there may be no escape. Even more dangerous than supernovae are gamma-ray bursts. These are the most luminous explosions in the universe, capable of releasing more energy in a few seconds than the Sun will emit in its entire lifetime. And if one were to occur in the Milky Way, pointed toward Earth, the consequences could be apocalyptic. Gamma-ray bursts come in 2 main types: short-duration bursts lasting less than 2 seconds, are thought to result from the merger of 2 neutron stars or a neutron star and a black hole. Long-duration bursts lasting more than 2 seconds are associated with the collapse of extremely massive stars, a special type of supernova called a hypernova. During a gamma-ray burst, 2 narrow jets of material are launched from the collapsing core at nearly the speed of light. These jets produce intense beams of gamma rays. If one of these beams happens to point toward Earth, we see a gamma ray burst. The energy in these beams is staggering. A gamma ray burst releases more energy in a few seconds than the entire Milky Way emits in the same time period. Most of this energy is concentrated in the narrow jets, making them especially dangerous to anything in their path. If a gamma ray burst were to occur within a few thousand light-years of Earth, with its jet pointed toward us, the effects would be devastating. The gamma ray flux would be thousands or millions of times stronger than from a nearby supernova. This radiation would strip away Earth's ozone layer within seconds. The surface would be exposed to intense solar ultraviolet radiation. Photosynthesis would be disrupted. Marine ecosystems, which depend on organisms living near the ocean surface, would collapse. The gamma rays would also ionize the upper atmosphere, creating nitrogen oxides that would further deplete ozone. The atmospheric effects would persist for years, leading to a prolonged period of high surface radiation and disrupted climate. Some scientists have speculated that past mass extinction events on Earth may have been triggered by distant gamma ray bursts. The Ordovician extinction, about 445 million years ago, has been tentatively linked to a gamma ray burst, though the evidence is not conclusive. Fortunately, gamma ray bursts are extremely rare. In a galaxy like the Milky Way, they are estimated to occur roughly once every 100,000 to 1 million years. And because the jets are narrow, the chance that one will be pointed directly at Earth is very small. Astronomers monitor stars that could potentially produce gamma ray bursts. These include certain types of massive stars with rapid rotation, known as Wolf-Rayet stars. If such a star is oriented with its rotation axis pointing toward Earth, its eventual collapse could produce a gamma ray burst aimed our way. One such star, WR104, located about 8,000 light-years away, has been identified as a possible threat. Its rotation axis may be pointed roughly in our direction. If it were to collapse into a gamma ray burst, we could be in the danger zone. However, measurements of WR104's orientation are uncertain. It may not be pointed at us after all, and even if it is, the star may not produce a gamma ray burst when it dies. Many massive stars collapse without producing jets. The threat from gamma ray bursts extends beyond Earth. Any life anywhere in the Milky Way is potentially at risk. The beams from these explosions can reach across thousands of light-years, sterilizing entire regions of the galaxy. This may have implications for the distribution of life in the galaxy. Regions with high rates of massive star formation, such as the spiral arms, may experience more frequent gamma ray bursts. This could make these regions less hospitable to the long-term survival of complex life. Gamma ray bursts represent one of the universe's most powerful and indiscriminate weapons. They are cosmic snipers, capable of extinguishing life across vast distances with no warning. Their rarity is fortunate, but over the billions of years of the Milky Way's history, these events have likely occurred many times, reshaping the possibilities for life in the galaxy. The Milky Way is embedded in a vast halo of dark matter. This invisible substance makes up most of the galaxy's mass, and its gravitational influence holds the galaxy together. But dark matter may pose subtle threats that we are only beginning to understand. Dark matter does not interact with ordinary matter through electromagnetic forces. It does not emit, absorb, or reflect light. It interacts only through gravity, and possibly through weak nuclear forces. This makes it extremely difficult to study. But dark matter is not entirely passive. Its gravitational effects shape the galaxy's evolution. Clumps and streams of dark matter flow through the galactic disk, exerting tiny gravitational tugs on stars and gas clouds. Over long periods of time, these perturbations could affect stellar orbits. A dense clump of dark matter passing through the solar neighborhood could alter the orbits of comets in the distant Oort cloud, potentially sending some of them toward the inner solar system. Some scientists have proposed that periodic comet bombardments in Earth's history may be linked to the solar system's passage through dark matter structures. As the Sun orbits the galaxy, it passes through the galactic plane every 30 to 40 million years, where dark matter density may be higher. This passage could disturb the Oort cloud, triggering comet showers that increase the rate of impacts on Earth. Some mass extinction events in the fossil record show a possible periodic pattern that might correlate with these crossings. However, this hypothesis remains controversial. The evidence for periodicity in extinction events is not strong, and the density of dark matter in the galactic plane is uncertain. Dark matter may also interact with itself in ways we do not yet understand. Some theories propose that dark matter particles can collide and annihilate, producing high-energy particles or radiation. If this occurs in the galactic halo, it could affect the galaxy in subtle ways. Annihilation events could heat the dark matter halo, causing it to expand. This would slightly weaken the gravitational binding of the galaxy, potentially affecting the stability of the disk. Dark matter annihilation could also produce cosmic rays. These particles would add to the existing cosmic ray population, potentially increasing the radiation environment in the galaxy. Another possibility is that dark matter interacts with ordinary matter through rare, weak interactions. If dark matter particles occasionally collide with atomic nuclei, these collisions could deposit energy and matter. In stars, dark matter collisions could provide an additional source of heat, potentially extending the lifetime of stars or altering their evolution. In very dense environments such as the cores of neutron stars, dark matter capture and annihilation could be significant. Dark matter might even form dense structures within stars or planets. If dark matter particles can lose energy through interactions, they could be captured by gravitational fields and sink to the centers of massive objects, forming dark matter cores. These cores would add to the gravitational field of the object, but would be otherwise invisible. In extreme cases, a dark matter core could become dense enough to collapse into a black hole, potentially consuming the host object from the inside. These scenarios are speculative, based on theories of dark matter that go beyond the simplest models, but they highlight that we do not fully understand dark matter's role in the galaxy. The greatest threat from dark matter may simply be our ignorance. We know it is there. We know it shapes the galaxy, but we do not know its fundamental nature, and without that knowledge, we cannot predict all the ways it might affect the Milky Way's future. The space between galaxies is not empty. It contains diffuse gas, much of it left over from the formation of galaxies in the early universe. Occasionally, large clouds of this gas are detected moving through intergalactic space, and if one of these clouds were to collide with the Milky Way, the impact could have significant consequences. High-velocity clouds are large concentrations of neutral hydrogen gas observed moving at speeds inconsistent with normal galactic rotation. Many are thought to be clouds of gas falling into the Milky Way from the intergalactic medium. Most high-velocity clouds are relatively small and diffuse. When they impact the galactic disk, they are quickly dissipated and incorporated into the disk's gas supply. This accretion is actually beneficial, providing fresh material for future star formation. But not all infalling clouds are small. Some models suggest that much larger clouds could exist, perhaps remnants of gas stripped from galaxies during past interactions or left over from the early universe. If a truly massive gas cloud were to collide with the Milky Way, the impact could be dramatic. The cloud would crash into the galactic disk at high speed, compressing the gas and triggering intense bursts of star formation. This starburst could dramatically increase the supernova rate in the affected region. The sudden influx of energy from many supernovae could heat the disk, driving a powerful galactic wind and potentially blowing gas out of the galaxy. Such an event might even disrupt the spiral structure of the galaxy. The compression and heating from the impact could create disturbances that propagate through the disk, temporarily altering the density wave patterns that maintain the spiral arms. Evidence for past cloud impacts may exist in the structure of the Milky Way. Some features in the galactic disk, such as vertical density waves or unusual stellar populations, might be remnants of ancient collisions with intergalactic clouds. There is also the possibility of truly catastrophic clouds. In the early universe, conditions were very different. Gas was more abundant, and large-scale structures were still forming. Some theories propose that giant clouds of primordial gas might still be falling toward galaxies from that era. If such a cloud, with mass comparable to billions of stars, were to impact the Milky Way, the collision could rival a dwarf galaxy merger in its effects. The galaxy structure would be significantly altered. The disk could be thickened or even disrupted. Such massive clouds are hypothetical, and observations have not confirmed their existence in the nearby universe. But the possibility cannot be entirely ruled out. Even without massive clouds, the ongoing accretion of smaller clouds poses a continuous low-level threat. Each impact deposits energy into the disk. Over time, the cumulative effect of many impacts contributes to the heating and thickening of the disk. This heating gradually increases the velocity dispersion of stars in the disk, causing them to move more randomly rather than in orderly circular orbits. This process, called dynamical heating, slowly erodes the thin, organized structure of the galactic disk. In a sense, the Milky Way is under constant bombardment from the intergalactic medium. Each infalling cloud is a small impact, gradually wearing away at the galaxy's structure over billions of years. The space between stars is not completely empty. Drifting through the galaxy are rogue planets, objects that were ejected from their parent star systems and now wander alone through the darkness. These interstellar wanderers pose an unpredictable threat to planetary systems throughout the Milky Way. Rogue planets are thought to be common in the galaxy. Computer simulations of planetary system formation suggest that many planets are ejected during the chaotic early stages when multiple planets interact gravitationally. The gravitational dance between forming planets can result in some being flung out of the system entirely. Estimates suggest there may be billions or even trillions of rogue planets in the Milky Way, potentially outnumbering the stars themselves. These dark, frozen worlds drift through interstellar space, invisible except when they happen to pass in front of a background star. Most rogue planets are thought to be gas giants, similar to Jupiter or Neptune. These massive planets are more easily ejected from their systems because of their strong gravitational interactions with other planets. Rocky planets like Earth can also be ejected, though perhaps less commonly. A rogue planet travelling through interstellar space would be incredibly cold. Without a star to warm it, the surface temperature would drop to just a few degrees above absolute zero. Any atmospheres would freeze solid. Oceans would become ice kilometers thick. The danger from rogue planets comes from their potential to pass through or near other star systems. If a Jupiter-mass rogue planet were to pass through the outer regions of a star system, its gravity could disrupt the orbits of planets, comets, and asteroids. The Oort clouds surrounding our solar system would be particularly vulnerable. This distant shell of comets extends perhaps 1 light year from the Sun. A rogue planet passing through this region could gravitationally scatter thousands of comets, sending some toward the inner solar system. Such a disturbance could trigger a comet shower lasting millions of years. The increased rate of impacts on Earth and other inner planets could have catastrophic consequences for any life present. Mass extinctions could result from the impacts and the climate changes they cause. The probability of a rogue planet passing close enough to our solar system to cause significant disruption is low but not zero. Over the billions of years of the solar system's history, such encounters may have occurred multiple times. Some scientists have proposed that past mass extinctions on Earth could be linked to rogue planet encounters. The evidence is circumstantial, but the possibility cannot be ruled out entirely. Beyond rogue planets, there are also smaller interstellar objects. In 2017, astronomers detected Oumuamua, the first confirmed interstellar object passing through our solar system. This cigar-shaped object, perhaps a few hundred meters long, travelled through the inner solar system at high speed before departing back into interstellar space. Oumuamua's nature remains mysterious. It showed some anomalous acceleration that could not be explained by gravity alone, leading to speculation about its composition and origin. Some suggested it might be a fragment of a larger object, while others proposed more exotic explanations. In 2019, a second interstellar object, Comet 2I Borisov, was detected. This one clearly showed cometary activity, confirming it as an icy body from another star system. Its chemical composition was analysed and found to be similar to comets in our own solar system. These discoveries confirmed that interstellar objects regularly pass through the solar system. Most are too small or too faint to detect, but they are there, silent visitors from distant stellar neighbourhoods. If a large interstellar object were to collide with Earth, the consequences would be devastating. An object even a few kilometres across travelling at interstellar speeds would impact with tremendous energy, potentially causing a global catastrophe. The closing speed between the solar system and interstellar objects can be very high. While objects within the solar system typically move at tens of kilometers per second relative to each other, interstellar objects can approach at speeds of 50 to 100 kilometers per second or more. This high relative velocity means that even small objects carry enormous kinetic energy. A 1 kilometer object traveling at 70 kilometers per second would impact with the energy of millions of nuclear weapons. The probability of such an impact is extremely low. Space is vast, and even with billions of rogue planets and countless smaller objects, the chance of a direct collision with Earth is minuscule. But over the lifetime of the galaxy, such events are inevitable somewhere. Rogue planets and interstellar objects represent a chaotic element in the galaxy. They are difficult to detect and track. They appear suddenly and disappear just as quickly. They are reminders that the galaxy is not an orderly, predictable place, but a dynamic environment full of wandering objects. For any advanced civilization attempting to explore or colonize the galaxy, rogue planets could be both a hazard and an opportunity. They are hazards because of the disruption they can cause, but they are also opportunities, potentially harboring subsurface oceans heated by tidal forces or radioactive decay, making them potential refuges for life. The Milky Way is filled with these dark wanderers. They drift silently through the void, invisible monuments to violent planetary system dynamics. They connect star systems in unexpected ways, occasionally passing through, leaving subtle gravitational signatures, then moving on into the darkness. The Milky Way is pervaded by cosmic rays, high-energy particles streaming through space at nearly the speed of light. These particles, mostly protons and atomic nuclei, pose a subtle but persistent threat to biological systems and to the structure of the interstellar medium. Cosmic rays are produced primarily by supernova explosions. The shock waves from these explosions accelerate particles to extreme energies, launching them into the galaxy. Once created, cosmic rays can travel through the galaxy for millions of years before escaping or losing energy. The energy density of cosmic rays in the Milky Way is comparable to the energy density of starlight and magnetic fields. They are a major component of the galaxy's energy budget, and their pressure affects the dynamics of the interstellar medium. Cosmic rays ionize the gas they pass through. This ionization affects the chemistry of molecular clouds, enabling reactions that would not occur in neutral gas. In this way, cosmic rays influence the process of star formation. But cosmic rays also pose a danger. Their high energies make them damaging to biological molecules. Prolonged exposure to cosmic rays can cause mutations in DNA, potentially leading to cancer or other genetic damage. On Earth, we are largely protected from cosmic rays by the Sun's magnetic field and Earth's atmosphere. But in space, or on worlds without protective atmospheres, cosmic rays are a significant hazard. For any future space travelers or colonists on other worlds, cosmic ray shielding will be essential. The background cosmic ray flux in the galaxy is manageable with proper shielding. But near sources of cosmic rays, such as recent supernova remnants, the flux can be much higher and far more dangerous. Cosmic rays may also affect the habitability of regions within the galaxy. Areas with high cosmic ray fluxes, such as the inner galaxy near the galactic center, may be less hospitable to life. The constant radiation could make it difficult for complex organisms to survive. Some scientists have proposed that cosmic rays could limit the galactic habitable zone, the region of the galaxy where conditions are favorable for life. This zone might exclude the inner regions, where cosmic ray fluxes are high, and the outer regions, where heavy elements needed for planets are scarce. Cosmic rays also affect the galaxy itself. They provide pressure support in molecular clouds, helping to resist gravitational collapse. This can slow the rate of star formation, regulating the galaxy's activity. In extreme cases, cosmic ray pressure can drive galactic winds. If cosmic rays accumulate in a region, their pressure can push gas outward, launching an outflow. This process may be important in regulating the growth of galaxies by expelling gas that could otherwise form stars. Very high-energy cosmic rays, called ultra-high-energy cosmic rays, are particularly mysterious. These particles carry energies far beyond what supernova shocks can produce. Their origin is unknown, though some may come from outside the Milky Way. If ultra-high-energy cosmic rays are produced within the galaxy, perhaps by the supermassive black hole or by some other exotic source, they could pose a significant threat. A single ultra-high-energy cosmic ray carries as much energy as a baseball thrown at high speed, all concentrated in a single atomic nucleus. The impact of such a particle with the atmosphere of a planet would create a cascade of secondary particles, a cosmic ray shower. While a single such event is unlikely to cause widespread damage, a high flux of ultra-high-energy cosmic rays could be catastrophic. Cosmic rays remind us that space is not empty and benign. It is filled with energetic particles, remnants of violent events, streaming through the galaxy at nearly the speed of light. They are a constant, invisible threat to life and a shaping force in the evolution of the galaxy. In the vast expanse of the Milky Way's disk, stars are typically separated by several light years. This immense distance makes direct collisions between stars extremely rare under normal circumstances, but in certain environments stellar encounters become a real threat. Globular clusters are among the densest stellar environments in the galaxy. These ancient clusters contain hundreds of thousands to millions of stars packed into a volume only a few dozen light-years across. In the cores of globular clusters, stars are separated by mere light weeks or light days. In such crowded conditions, stellar encounters become common. Close passages between stars can alter orbits, exchange energy, and occasionally lead to direct collisions. When two stars collide, they merge, forming a single, more massive star. These collision products, called blue stragglers, are observed in globular clusters. They appear younger than the cluster's other stars because the collision mixes fresh hydrogen into the core, temporarily reigniting nuclear fusion. But collisions can also be destructive. A collision at high speed could partially disrupt both stars, ejecting material into space. Any planets orbiting either star would be destroyed or flung into new, likely unstable orbits. The galactic center is another environment where stellar encounters are frequent. The central star cluster surrounding Sagittarius A star is extremely dense. Stars here orbit at high speeds in a tight volume around the black hole. Encounters between stars in the galactic center can lead to exotic outcomes. If two stars collide and merge near the black hole, the resulting star might be massive enough to collapse into a black hole itself, adding to the population of stellar mass black holes orbiting the supermassive black hole. Close encounters can also result in gravitational capture. Two stars passing close to each other, especially near the supermassive black hole, can become bound in a binary system. These binaries are then subject to further encounters, leading to complex dynamical evolution. During the Andromeda collision, stellar encounters will become much more common throughout the Milky Way. As the two galactic disks pass through each other, the local stellar density will temporarily increase dramatically. Though direct collisions will still be rare, close encounters will become frequent. Stars will have their orbits perturbed, planets will be scattered, and some planetary systems will be disrupted entirely. Computer simulations of the Milky Way Andromeda merger show that our solar system will likely survive the event without a direct collision, but there is a small chance of a close encounter with a star from Andromeda, which could disturb the outer planets or the Oort cloud. Stellar encounters can also affect star formation. If two stars pass through a molecular cloud, their gravity can compress the gas, potentially triggering collapse and starbirth. Or they can disrupt the cloud, preventing stars from forming. In the early universe, when galaxies were smaller and more densely packed with gas and stars, stellar encounters were much more common. The high collision rate may have influenced the types of stars that formed and the overall evolution of early galaxies. Today, in the relatively calm environment of the galactic disk, stellar encounters are rare. Our Sun will likely complete its entire lifetime without a close encounter with another star. But over the 10 billion year history of the galaxy, many stars have not been so fortunate. Each encounter is a cosmic lottery. Most result in nothing more than slightly altered orbits. But occasionally, an encounter can be catastrophic, destroying planetary systems, disrupting binaries, or even leading to stellar collisions that reshape both stars involved. Throughout the Milky Way, there are thousands of stellar mass black holes, remnants of massive stars that have collapsed. Most are solitary, quietly orbiting the galaxy. But some exist in binary systems, and these systems pose a unique threat. When two black holes orbit each other, they slowly lose energy through the emission of gravitational waves. These ripples in space-time carry energy away from the system, causing the orbits to decay. Eventually, the black holes spiral together and merge. Black hole mergers are among the most violent events in the universe. In the final moments before merger, the black holes orbit each other thousands of times per second. The gravitational wave emission becomes intense, releasing more energy than all the stars in the visible universe combined. When the black holes finally merge, they form a single larger black hole. The merger is not smooth. The collision creates powerful oscillations in the fabric of space-time, and some of the mass is converted directly into gravitational wave energy. These gravitational waves propagate outward at the speed of light. If a black hole merger were to occur relatively close to the solar system, the passing gravitational wave could be detected by instruments on Earth. Advanced LIGO and other gravitational wave observatories have already detected dozens of black hole mergers, all occurring in distant galaxies. But someday, a merger will occur within the Milky Way, perhaps within a few thousand light-years of Earth. The gravitational wave from such an event would be much stronger than those detected from distant galaxies. It would cause measurable distortions in space-time as it passed through Earth, stretching and compressing space by a tiny fraction. These distortions are far too small to directly affect matter. The stretching is at the level of 1 part in a trillion. But the energy in the gravitational wave is real, and in principle it could have subtle effects on sensitive systems. The greater threat from black hole mergers comes from their electromagnetic counterparts. If the black holes are surrounded by gas, the merger can trigger a burst of radiation. This electromagnetic flare could be dangerous if it occurs nearby. Binary systems containing a black hole and a neutron star are particularly interesting. When such systems merge, the neutron star is torn apart by tidal forces just before being swallowed by the black hole. This creates a brief but intense burst of radiation. These neutron star black hole mergers may be the source of some short gamma-ray bursts. If such a merger were to occur within the Milky Way and produce a burst pointed toward Earth, the effects could be significant. The most dramatic black hole merger in the Milky Way's future will be the merger of the supermassive black holes from the Milky Way and Andromeda. When the two galaxies fully merge, their central black holes will eventually spiral together over hundreds of millions of years. The merger of two supermassive black holes, each containing millions of solar masses, will be an event of unprecedented power. The gravitational waves will be detectable across the universe. Any civilization observing from a safe distance will witness a cosmic spectacle, but the immediate environment will be anything but safe. The merger will occur at the center of the newly formed elliptical galaxy. Any stars orbiting nearby will be subjected to intense gravitational forces, their orbits violently disturbed. The final moments of the merger will release a burst of gravitational waves so powerful that space-time itself will oscillate violently in the central region. This could scatter stars into new orbits, or even eject some stars from the galaxy entirely. Black hole mergers are rare but inevitable. They represent the final fate of massive binary systems, and they are a reminder that even in the seemingly empty void of space, the most violent events imaginable are taking place, shaping the evolution of galaxies across cosmic time. Today, the Milky Way's supermassive black hole is quiet, accreting material at a very low rate. But this has not always been the case, and it may not remain so forever. The black hole has the potential to enter an active phase, becoming an active galactic nucleus with profound consequences for the entire galaxy. An active galactic nucleus, or AGN, occurs when a supermassive black hole actively consumes large amounts of material. The infalling matter forms a bright accretion disk and can launch powerful jets of material outward at nearly the speed of light. During an AGN phase, the central region of the galaxy becomes incredibly luminous. The accretion disk can outshine all the stars in the galaxy combined. The radiation output spans the entire electromagnetic spectrum, from radio waves to gamma rays. This radiation poses a threat to the surrounding galaxy. High-energy X-rays and ultraviolet light from the AGN ionize gas throughout the inner galaxy. This ionization heats the gas, potentially preventing it from cooling and collapsing to form new stars. AGN-driven winds can also blow gas out of the galaxy entirely. The radiation pressure and the mechanical energy from the jets can launch massive outflows, removing the fuel for future star formation. This process, called AGN feedback, is thought to be crucial in regulating galaxy growth. Without it, galaxies would convert gas into stars too efficiently, forming much larger galaxies than we observe. But for any life in the galaxy, an AGN phase would be catastrophic. The intense radiation would sterilize large regions of the inner galaxy. Any planets within a few thousand light-years of the galactic center would be exposed to lethal doses of high-energy radiation. The Milky Way has likely experienced AGN phases in the past. The Fermi bubbles are evidence of a burst of activity a few million years ago. Other structures in the galactic halo may be remnants of earlier episodes. Future AGN activity could be triggered by several mechanisms. The infall of a large gas cloud toward the galactic center could feed the black hole. The disruption of a star cluster near the black hole could provide material, or the merger with the Large Magellanic Cloud or Andromeda could funnel gas toward the center. The Andromeda merger is particularly likely to trigger AGN activity. Galaxy mergers often drive gas toward the central regions through gravitational torques. Both the Milky Way's and Andromeda's black holes could become active during the merger. When the two supermassive black holes eventually merge, the resulting black hole will be highly disturbed. The merger will create oscillations in the black hole structure, and surrounding material will be heated and expelled. This post-merger activity could create a brief but intense AGN phase. The duration of an AGN phase depends on the fuel supply. If a large reservoir of gas is available, the AGN could remain active for millions of years. If the fuel is quickly exhausted, the AGN might last only tens of thousands of years. During an active phase, the galaxy would look very different. A brilliant point of light would dominate the center, visible even from the outer edges of the galaxy. Jets might extend above and below the galactic plane, creating huge lobes of radio emission. The environmental effects would reshape the inner galaxy. Star formation would be suppressed or halted in the central regions. The existing stellar population would be bathed in intense radiation, and the structure of the interstellar medium would be dramatically altered. An AGN phase represents one of the most extreme threats the Milky Way could face from internal processes. It would transform the galaxy from a peaceful spiral into a cosmic powerhouse, with consequences extending for millions of years after the activity ceased. Throughout the Milky Way, massive stars are approaching the end of their lives. Some of these stars are relatively close to our solar system. When they explode as supernovae, the effects could be significant for Earth and the surrounding region of the galaxy. Astronomers maintain a list of supernova candidates, massive stars that could explode at any time on cosmic timescales. Any time, in astronomical terms, means within the next million years or so. Pinpointing exactly when a star will explode is difficult because the final stages of stellar evolution are complex and chaotic. One of the most famous supernova candidates is Betelgeuse, a red supergiant in the constellation Orion. Betelgeuse is about 600 to 700 light-years from Earth, making it one of the closer massive stars. Betelgeuse is a variable star, meaning its brightness changes over time. In late 2019 and early 2020, Betelgeuse underwent an unusual dimming event, dropping to about 40% of its normal brightness. This led to speculation that the star might be about to explode. However, subsequent observations suggested the dimming was caused by dust clouds ejected from the star's surface, which temporarily blocked our view. Betelgeuse returned to its normal brightness, and while it will certainly explode someday, that day may still be thousands or even hundreds of thousands of years away. If Betelgeuse were to explode, it would be a spectacular sight from Earth. The supernova would be visible in daylight, shining as brightly as the full moon, or even brighter. It would remain visible for weeks or months before gradually fading. At 600 light-years distance, Betelgeuse is far enough that the supernova would not pose a direct danger to Earth. The radiation and particle flux would be attenuated by distance to levels that would not significantly affect our planet's atmosphere or biosphere. However, not all nearby supernova candidates are so distant. Spica, the brightest star in the constellation Virgo, is another massive star that will eventually explode. It lies about 250 light-years away, closer than Betelgeuse. Antares, the bright red star in Scorpius, is yet another supergiant that will become a supernova. It is about 550 light-years away. Like Betelgeuse, it is a red supergiant in the late stages of its life. Ik Pegasi is a binary star system about 150 light-years from Earth. It contains a white dwarf that is accreting material from its companion star. If the white dwarf gains enough mass, it could explode as a Type Ia supernova. Type Ia supernovae are different from the core collapse supernovae that massive stars undergo. They occur when a white dwarf in a binary system accumulates enough material to exceed a critical mass limit, causing a runaway thermonuclear explosion. Type Ia supernovae are somewhat less energetic than core collapse supernovae, but they are still powerful. At 150 light-years, an Ik Pegasi supernova would be bright enough to be visible during the day, but still too distant to cause serious damage to Earth. The danger zone for supernovae is generally considered to be about 50 light-years or less. Within this distance, the radiation and cosmic ray flux from a supernova could significantly affect Earth's atmosphere, potentially damaging the ozone layer and exposing the surface to increased ultraviolet radiation. Fortunately, there are no known massive stars or white dwarf binaries within 50 light-years of Earth that are likely to explode in the near future. The nearest massive star, Sirius, is only 8.6 light-years away, but it is not massive enough to become a supernova. It will eventually become a white dwarf, but that is billions of years away. However, our knowledge of nearby stars is not complete. There could be stars or stellar remnants nearby that have not been detected. Dim red dwarfs, brown dwarfs, and isolated white dwarfs could lurk in our cosmic neighbourhood unnoticed. More concerning are stars whose motions will bring them closer to Earth in the future. Stars are constantly moving through the galaxy. Some stars currently far away will pass relatively close to the solar system in the future. Astronomers use astrometry, the measurement of stellar positions and motions, to predict future close approaches. The Gaia spacecraft has provided precise measurements of positions and motions for over 1 billion stars, allowing detailed predictions of stellar trajectories. Some stars will pass within a few light-years of the Sun over the next few million years. If any of these stars are massive enough or are white dwarfs in binary systems, they could pose future supernova threats. The star Gliese 710, a red dwarf currently about 63 light-years away, will pass within about 10,000 astronomical units of the Sun in about 1.3 million years. While Gliese 710 is not massive enough to become a supernova, its close passage could disturb the Oort cloud, triggering a comet shower. The threat from nearby supernovae is not immediate, but it is real over the timescales of millions of years. The Milky Way has a supernova rate of 1 to 3 per century. Over millions of years, thousands of supernovae will occur in the galaxy. Statistical calculations suggest that Earth experiences a nearby supernova within 50 light-years, roughly once every few hundred million years. The last such event may have been about 2 to 3 million years ago, possibly coinciding with climate changes and extinctions in Earth's fossil record. Evidence for past nearby supernovae comes from isotopes found in deep-sea sediments. Iron-60, a radioactive isotope with a half-life of about 2.6 million years, has been detected in sediment layers dating to about 2 to 3 million years ago. Iron-60 is produced in supernovae but not in significant quantities by other processes. Its presence in marine sediments suggests that supernova ejecta reached Earth, depositing this isotope on the ocean floor. The supernova that produced this Iron-60 was likely part of the Scorpius-Centaurus Association, a group of young, massive stars located a few hundred light-years from Earth. One or more stars in this association exploded as supernovae, and the expanding debris eventually reached our solar system. The effects of this supernova on Earth were likely subtle. There is no evidence of mass extinctions coinciding with the Iron-60 deposits, but there may have been increased cosmic ray flux, auroral activity, and possibly minor climate effects. Future nearby supernovae are inevitable. The question is not if, but when and how close. Each supernova candidate in our cosmic neighborhood is a potential threat, a massive star on the brink of explosion, counting down to a moment that could reshape the radiation environment of nearby space. For now, we watch and wait. Astronomers monitor the supernova candidates, measuring their properties, tracking their evolution. When the next nearby supernova occurs, we will be ready to observe and analyze, learning from the event even as we assess any impacts on our planet and our solar system. Permeating the Milky Way is a sea of high-energy particles called cosmic rays. These particles, primarily protons and atomic nuclei, travel at nearly the speed of light, spiraling along the galaxy's magnetic field lines. Though invisible, cosmic rays play a crucial role in the galaxy's invisible architecture. Cosmic rays are accelerated to their tremendous energies by supernova explosions. When a massive star explodes, the shock wave from the explosion accelerates particles to relativistic speeds. These particles escape into the interstellar medium, spreading throughout the galaxy. The energy density of cosmic rays in the Milky Way is comparable to the energy density of the magnetic field, the turbulent gas motions and the starlight. Cosmic rays are a significant component of the galaxy's energy budget. As cosmic rays stream through the galaxy, they interact with gas, dust, and magnetic fields. These interactions transfer energy and momentum, influencing the dynamics of the interstellar medium. Cosmic rays provide pressure support in gas clouds. In regions where cosmic ray pressure is high, it can counteract gravity, slowing or preventing the collapse of clouds into stars. This regulates the rate of star formation. Cosmic rays also ionize the interstellar medium. When a high-energy cosmic ray particle collides with a neutral hydrogen atom, it can knock an electron free, ionizing the atom. This ionization affects the chemistry of the interstellar medium, enabling reactions that would not occur in neutral gas. In molecular clouds, where most atoms are shielded from starlight by dust, cosmic rays are the primary source of ionization. This ionization drives a complex chemistry that produces a rich variety of molecules, from simple carbon monoxide to complex organic compounds. Cosmic rays also couple gas to magnetic fields. The ionization they create makes the gas electrically conductive. The magnetic field lines and the ionized gas become locked together, moving as one. This coupling affects how gas flows through the galaxy and how magnetic fields are amplified. The propagation of cosmic rays through the galaxy is controlled by the magnetic field. Cosmic rays spiral along field lines, effectively trapped by the magnetic forces. This confinement keeps cosmic rays within the galaxy for millions of years before they escape into intergalactic space. During their time in the galaxy, cosmic rays diffuse slowly, bouncing off magnetic irregularities and scattering through the interstellar medium. This diffusion spreads cosmic rays throughout the galaxy, creating a relatively uniform distribution. However, there are local variations. Near supernova remnants and other sites of particle acceleration, cosmic ray densities are higher. These regions glow in gamma rays, produced when cosmic rays collide with gas and produce high-energy photons. Observations of gamma-ray emission from the galactic plane allow astronomers to map the distribution of cosmic rays and the gas they interact with. These observations reveal the structure of the galaxy's spiral arms and the locations of molecular clouds. Cosmic rays also escape from the galaxy. They can diffuse out of the disk into the halo and eventually into the intergalactic medium. This escape removes energy from the galaxy, contributing to galactic outflows. The escape of cosmic rays is thought to drive galactic winds. The pressure gradient created by cosmic rays escaping from the disk can push gas outward, launching a wind that carries matter and energy into the halo. This wind is most effective in regions with high supernova rates, where cosmic ray production is high. In the central regions of the galaxy, where star formation is more intense, the cosmic ray-driven wind may be stronger. Cosmic rays reaching Earth provide a direct sample of the galactic environment. By studying these particles, scientists can learn about the conditions in distant parts of the galaxy, about the processes that accelerate particles, and about the composition of the interstellar medium. Some cosmic rays are more exotic. A small fraction are electrons and positrons, rather than protons and nuclei. An even smaller fraction are antiprotons, antimatter particles. The origins of these particles are still being investigated. Cosmic rays are also thought to play a role in the heating of the interstellar medium. When cosmic rays collide with gas, they deposit energy, heating the gas. This heating can balance the cooling from radiation, maintaining a warm, diffuse phase of the interstellar medium. The invisible architecture of cosmic rays connects many aspects of the galaxy. They link supernovae to star formation, magnetic fields to gas dynamics, and the disk to the halo. Understanding cosmic rays is essential for understanding the Milky Way as an interconnected system. The disk of the Milky Way is not perfectly flat. At large distances from the galactic center, the disk warps, bending upward on one side and downward on the other. This warp is a large-scale distortion of the disk's geometry, part of the galaxy's invisible architecture. The warp becomes noticeable at distances beyond about 50,000 light-years from the center. In the inner galaxy, the disk is relatively flat, but farther out, it deviates significantly from the plane defined by the inner disk. The amplitude of the warp increases with distance. At the edge of the observed disk, the warp can displace the disk vertically by several thousand light-years. This creates a twisted, bent structure rather than a flat plane. The warp is not unique to the Milky Way. Many spiral galaxies show similar warps in their outer disks. In fact, warps appear to be the norm rather than the exception, suggesting they are a natural consequence of galaxy formation and evolution. The cause of the Milky Way's warp is still debated. Several mechanisms have been proposed, each involving the invisible architecture of the galaxy. One possibility is that the warp is caused by tidal interactions with satellite galaxies. The Large Magellanic Cloud, in particular, is massive enough that its gravity could distort the outer disk of the Milky Way. As the Large Magellanic Cloud orbits the Milky Way, its gravitational pull tugs on the disk, bending it out of plane. Computer simulations show that such tidal interactions can produce warps similar to what is observed. Another possibility is that the warp is caused by the misalignment of the galactic disk with the dark matter halo. If the halo is not perfectly aligned with the disk, its gravity can torque the disk, causing it to precess and warp. This misalignment could result from the accretion of gas or dark matter with angular momentum oriented differently from the disk. Over time, the accumulated misaligned material would exert a net torque on the disk. A third possibility involves the infall of gas from the intergalactic medium. If gas falls into the galaxy from a preferred direction, it could deposit angular momentum that tilts or warps the outer disk. The warp may also be a transient feature. If it is driven by interactions with satellites or misaligned accretion, it could evolve over time. Past interactions may have created warps that have since faded, and new interactions may create new warps in the future. Observations of the warp are challenging because it is difficult to measure vertical positions of stars at large distances. Astronomers use various techniques, including observations of neutral hydrogen gas, which extends farther than the stars and traces the warp clearly. Radio surveys of neutral hydrogen show the warp in detail, mapping how the disk bends as a function of position. These observations reveal that the warp is not symmetric. One side of the disk bends upward more than the other side bends downward. This asymmetry provides clues about the warp's origin. A symmetric warp might result from a simple torque or misalignment, while an asymmetric warp suggests a more complex interaction, perhaps involving a specific satellite galaxy passing through the disk. The warp also affects the kinematics of the outer disk. Stars and gas in the warped region have velocities that deviate from the simple, circular rotation of the inner disk. This creates a signature in the velocity field that can be used to study the warp structure. The warp may also influence the flow of gas in the outer galaxy. Gas clouds moving in the warped disk experience gravitational forces that differ from the forces in a flat disk. This could affect the rate of star formation in the outer regions. The warp is a reminder that galaxies are dynamic, evolving systems. They are not static, rigid structures, but flexible and responsive to gravitational influences. The outer disk of the Milky Way is sensitive to its environment, shaped by interactions with satellites and the surrounding dark matter halo. Understanding the warp helps astronomers understand the Milky Way's history. By modelling the warp and comparing it to observations, scientists can constrain the properties of the dark matter halo, the orbits of satellite galaxies, and the history of gas accretion. The warp also affects our view of the galaxy. Because we are located within the disk, the warp changes the distribution of stars and gas we see in different directions. This must be taken into account when constructing maps of the galaxy. The Milky Way does not exist in isolation. It is part of the local group, a small cluster of galaxies bound together by gravity. The gravitational influence of the local group shapes the evolution of the Milky Way, part of the galaxy's invisible architecture. The local group contains more than 80 galaxies. The two largest are the Milky Way and the Andromeda galaxy. The rest are smaller dwarf galaxies, many of which orbit the two giants. The Andromeda galaxy, also known as M31, is the nearest large spiral galaxy to the Milky Way. It lies about 2.5 million light-years away and is approaching the Milky Way at a speed of about 100 kilometers per second. This approach is driven by the mutual gravitational attraction of the two galaxies. Despite the expansion of the universe, which causes most distant galaxies to recede from us, the Andromeda galaxy and the Milky Way are close enough that gravity dominates over expansion. In about 4 billion years, the Milky Way and Andromeda will collide and merge. This merger will dramatically reshape both galaxies, triggering intense bursts of star formation, disrupting spiral structures, and eventually forming a single, larger elliptical galaxy. But even now, billions of years before the merger, the two galaxies influence each other. Their gravitational fields extend far beyond their visible boundaries, creating tidal forces that affect the motions of stars and gas in the outer regions. The gravity of Andromeda may be pulling the Milky Way, accelerating it slightly in the direction of the larger galaxy. This effect is subtle but measurable, and it affects the overall motion of the Milky Way through space. The local group also contains a third large spiral galaxy, Triangulum, also known as M33. Triangulum is smaller than the Milky Way and Andromeda, but is still a significant member of the group. Its gravitational influence contributes to the overall dynamics of the local group. The dwarf galaxies of the local group orbit the larger galaxies or move through the group's gravitational potential. Many are satellite galaxies of the Milky Way or Andromeda, held in orbit by the gravity of the larger galaxies. These satellites are not passive objects. Their gravity affects the Milky Way, perturbing the outer disk, stripping gas from the halo, and creating tidal streams. Each interaction between a satellite and the Milky Way leaves a mark. The collective gravitational pull of all the galaxies in the local group defines a common centre of mass. The Milky Way and Andromeda are both orbiting this centre, though they are also moving toward each other. The local group is embedded in a larger structure called the Virgo supercluster. This supercluster contains thousands of galaxies, and its gravity affects the motion of the local group as a whole. The local group is being pulled toward the centre of the Virgo supercluster by the collective gravity of the galaxies there. This motion adds a large-scale drift to the motion of the Milky Way through space. More recently, astronomers have discovered that the Virgo supercluster is itself part of an even larger structure called Laniakea. This immense supercluster contains over 100,000 galaxies and spans over 500 million light-years. The gravitational influence of Laniakea extends across this vast region, shaping the motions of galaxies on the larger scales. The Milky Way's motion is determined not just by its local environment, but by the distribution of matter across hundreds of millions of light-years. These large-scale structures are part of the cosmic web, the network of filaments and voids that defines the structure of the universe. Galaxies form along the filaments, and their motions are guided by the gravitational potential of the web. The Milky Way's position within the cosmic web influences its gas accretion. Gas flows along filaments toward galaxies, and the orientation and density of nearby filaments affect how much gas the Milky Way receives. The local group's environment is relatively quiet. We are not in a dense cluster of galaxies, where interactions and mergers are frequent and violent. This has allowed the Milky Way to evolve relatively undisturbed, forming a well-defined spiral structure. However, the upcoming merger with Andromeda will end this tranquility. The merger will be the most significant event in the Milky Way's history since its formation, reshaping the galaxy completely. Even now, the approach of Andromeda is affecting the Milky Way. Simulations suggest that the outer regions of the two galaxies' dark matter halos may already be interacting, even though the visible disks are still far apart. The influence of the local group reminds us that galaxies are not isolated islands. They are part of a larger cosmic ecosystem, connected by gravity, influenced by their neighbours, and embedded in the vast structure of the universe. The orbits of planets in the Milky Way are not perfectly stable over infinite time. Gravitational interactions between planets, passing stars, and galactic tides can slowly alter orbits, potentially leading to catastrophic instabilities that reshape or destroy planetary systems. Our own solar system appears stable on human timescales. The planets orbit the Sun in well-defined paths that have remained largely unchanged for billions of years. But computer simulations reveal that this stability is not guaranteed over extremely long periods. The orbits of planets are governed by the gravitational interactions between them. Each planet's gravity affects the others, creating a complex dynamical system. In systems with multiple planets, these interactions can lead to orbital resonances, where the orbital periods of planets are related by simple ratios. Resonances can be stabilizing or destabilizing. Some resonances lock planets into stable configurations that persist for the lifetime of the system. Others can amplify small perturbations, leading to chaotic dynamics and eventual orbital instability. The solar system is currently in a relatively stable configuration, but it is not immune to long-term instability. Simulations of the solar system's future evolution show that over timescales of billions of years, there is a small but non-zero probability of orbital chaos. Mercury's orbit is particularly susceptible to instability. Mercury's proximity to the Sun and its relatively high orbital eccentricity make it vulnerable to perturbations from other planets, especially Jupiter. Some simulations show scenarios where Mercury's orbit becomes increasingly eccentric over billions of years. Eventually, Mercury could either collide with Venus, collide with the Sun, or be ejected from the solar system entirely. If Mercury's orbit were to cross Venus's orbit, a collision between the two planets would release enormous energy. The impact would vaporize both planets, creating a massive debris cloud that could rain down on Earth and other inner planets. Such an event is extremely unlikely in the near future. The probability of Mercury going unstable within the next few billion years is estimated at only about 1%. But over the 10 billion year lifetime of the Sun, the cumulative probability becomes more significant. Beyond the solar system, planetary systems throughout the Milky Way face similar threats. Many exoplanetary systems discovered by astronomers have configurations that appear unstable on long timescales. Hot Jupiters, gas giant planets orbiting very close to their stars, likely migrated inward from more distant orbits. This migration was probably driven by gravitational interactions with other planets or with the protoplanetary disk. In many cases, this migration may have ejected or destroyed other planets in the system. Systems with multiple giant planets on relatively close orbits are particularly prone to instability. Over millions to billions of years, the planet's mutual gravitational interactions can lead to ejection of one or more planets or to collisions. Passing stars can also destabilize planetary orbits. When a star passes close to a planetary system, its gravity can perturb the planet's orbits. If the perturbation is strong enough, planets can be ejected from the system, or their orbits can be significantly altered. In dense stellar environments like globular clusters or the galactic center, stellar encounters are common. Planetary systems in these regions are constantly subjected to gravitational perturbations. This may explain why planets appear to be less common in globular clusters than in the galactic disk. Even in the galactic disk, where stellar densities are lower, encounters occur occasionally. Over the billions of years of a star's lifetime, it will likely experience at least one moderately close encounter with another star. The solar system has probably experienced such encounters in the past. Evidence suggests that the structure of the outer solar system, particularly the scattered disk of icy bodies beyond Neptune, may have been shaped by past stellar encounters. The next close encounter for the solar system will likely occur in about 1 million years, when the star Gliese 710 passes within about 10,000 astronomical units of the Sun. This is close enough to perturb the Oort cloud, but probably not close enough to significantly affect planetary orbits. However, over hundreds of millions of years, closer encounters will occur. Eventually, a star may pass within a few hundred astronomical units of the Sun, close enough to significantly perturb the outer planets or even destabilize their orbits. Galactic tides also affect planetary orbits, though more subtly. The gravitational field of the Milky Way is not uniform. As the solar system orbits the galaxy, it experiences varying tidal forces from the galactic mass distribution. These tides are strongest when the solar system passes through the galactic plane or through spiral arms. The periodic passage through the galactic plane every 30 to 40 million years subjects the solar system to enhanced tidal forces. Some scientists have proposed that these tidal variations could affect the orbits of distant comets in the Oort cloud, triggering periodic comet showers. The evidence for such periodicity is debated, but the mechanism is plausible. The long-term stability of planetary orbits is a subtle threat. It does not manifest as a sudden catastrophe, but as a gradual erosion of orbital predictability. Over billions of years, the cumulative effects of planetary interactions, stellar encounters, and galactic tides can reshape planetary systems. For the Milky Way as a whole, orbital instability means that planetary systems are constantly being created and destroyed. Planets are ejected, becoming rogue worlds drifting through interstellar space. Collisions create debris that may eventually coalesce into new planets. This ongoing process of destruction and creation is part of the galaxy's dynamical evolution. It ensures that planetary systems are not eternal structures, but transient configurations that change over cosmic time. The threat to any individual planet or planetary system is low on human timescales, but over the billions of years of galactic history, instability is inevitable. Every planetary system, including our own, faces the slow erosion of its orbital architecture. The invisible architecture of the Milky Way is not static. It evolves over time, shaped by internal processes and external influences. Looking forward, we can predict how this architecture will change over the next billions of years. The dark matter halo will continue to grow. As the Milky Way accretes smaller galaxies and dark matter subhalos, its halo will gain mass. This growth will strengthen the gravitational potential, affecting the motions of stars and gas. The bar structure at the galactic center may evolve. Bars can grow stronger or weaker depending on the flow of gas and stars in the inner galaxy. Future mergers or bursts of star formation could disrupt or reshape the bar. The spiral arms will shift and change. Spiral density waves are dynamic features that respond to changes in the galactic disk. As stars form and die, as gas flows through the galaxy, the spiral pattern will adjust. The magnetic field of the galaxy will continue to be amplified and tangled by the dynamo process. The field will grow stronger over time, though turbulence and outflows can disrupt and reorganize the field lines. The galactic fountain will continue to cycle gas between the disk and the halo. This process will regulate star formation, maintaining a steady but gradually declining rate of starbirth as the gas supply is consumed. The galactic corona will evolve as well. The balance between heating and cooling will shift depending on the rate of star formation and supernova explosions. If star formation declines, the corona may cool and condense, raining more gas onto the disk. The tidal streams from disrupted satellite galaxies will slowly mix into the galactic halo. Over time, the stars from these streams will lose their coherent structure and become part of the general stellar halo population. New satellites will be accreted and new streams will form. The Milky Way is still growing, still capturing smaller galaxies from its surroundings. This process will continue for billions of years. The warp in the outer disk may change. If it is driven by interactions with the Large Magellanic Cloud or other satellites, the warp structure will evolve as these satellites move and are disrupted. The sphere of influence of the central black hole will grow as the black hole accretes matter. Each star or gas cloud that falls into the black hole adds to its mass, increasing its gravitational pull and expanding the region it dominates. The cosmic ray population will fluctuate with the rate of supernovae. If star formation declines, fewer supernovae will occur and the cosmic ray density will drop. This could affect the heating and ionization of the interstellar medium. The most dramatic change will come from the merger with the Andromeda galaxy. When the two galaxies collide, their dark matter halos will merge first, creating a larger combined halo. The stellar disks will pass through each other, with stars rarely colliding, but their orbits being drastically perturbed. The spiral structures of both galaxies will be disrupted, and the disks will be pulled apart by tidal forces. Gas clouds will collide and compress, triggering massive bursts of star formation. These starbursts will light up the merge system with brilliant blue light from young, hot stars. Over hundreds of millions of years, the two galaxies will settle into a new configuration. The final product will likely be an elliptical galaxy, a smooth, featureless ball of stars with little ongoing star formation. The merged galaxy, sometimes called Milkomeda, will be larger and more massive than either the Milky Way or Andromeda alone. Its dark matter halo will extend farther, and its total mass will be the sum of the two galaxies. The supermassive black holes at the centers of the Milky Way and Andromeda will eventually merge as well. This merger will release tremendous energy in the form of gravitational waves, ripples in space-time that will propagate across the universe. After the merger, the architecture of Milkomeda will be very different from the Milky Way we know today. The spiral structure will be gone, replaced by a more random distribution of stars. The disk will be replaced by a spheroidal shape. Star formation will decline rapidly. Most of the gas will be consumed in the merger starbursts, and the remaining gas will be too hot or too diffuse to collapse into new stars. Milkomeda will become a red and dead galaxy, dominated by old stars. but this is billions of years in the future. For now, the Milky Way continues its steady evolution, its invisible architecture guiding the motions of stars and gas, shaping the galaxy we call home. The Milky Way resides within the cosmic web, the large-scale structure of the universe composed of filaments, sheets, and voids. The voids, vast regions of space with very little matter, are expanding as the universe expands. This expansion affects the environment of galaxies and poses a long-term threat to cosmic structure. Cosmic voids are enormous regions of space, typically 100 to 300 million light-years across, that contain very few galaxies. They are not completely empty, but their density is much lower than average. The voids are bounded by filaments and sheets of galaxies. These denser regions form the walls of the voids, creating a foam-like structure on the larger scales. The Milky Way lies within a filament, not inside a void, but the expansion of nearby voids affects our cosmic neighborhood. As the universe expands, the voids expand as well, growing larger over time. This expansion pushes matter away from the voids, concentrating it in the filaments and nodes where galaxies cluster. The local void, a relatively nearby underdense region, is expanding and affecting the motion of the local group. The Milky Way and Andromeda are being pushed away from the local void, contributing to the motion of the local group through space. On even larger scales, the expansion of voids is shaping the flow of galaxies across the universe. Galaxies move away from voids and toward denser regions, a process sometimes called void avoidance. The Milky Way's motion is influenced by several large-scale structures. The local void pushes us away. The Virgo cluster attracts us. The Shapley supercluster, an enormous concentration of galaxies about 650 million light-years away, also exerts a gravitational pull. The combined effect of these influences determines the Milky Way's peculiar velocity, its motion relative to the cosmic microwave background. This peculiar velocity is about 630 kilometers per second, directed toward the constellation Hydra. As voids continue to expand, the large-scale structure of the universe becomes more pronounced. The filaments become denser and more defined. The voids become emptier and larger. Eventually, in the far future, the accelerating expansion of the universe driven by dark energy will begin to dominate even on the scales of the cosmic web. The filaments will be pulled apart. Galaxy clusters will become isolated island universes. The expansion of voids represents a gradual fragmentation of cosmic structure. Matter is being organized on larger and larger scales, with increasingly empty regions between the concentrations of galaxies. For the Milky Way, the immediate effect of void expansion is minimal. The galaxy is safely within a filament surrounded by other galaxies. The local group is bound together by gravity, unaffected by the expansion of distant voids. But over tens of billions of years, as dark energy continues to drive acceleration, even the filaments will be affected. The space between galaxy groups will expand, eventually isolating each group from its neighbors. The local group will remain bound, but it will be increasingly isolated from other groups. The Virgo cluster, currently about 50 million light-years away, will recede beyond the cosmic horizon, disappearing from view as the space between us expands faster than light. Eventually, only the local group will be visible. The rest of the universe will have receded beyond reach, carried away by the accelerating expansion driven by dark energy. This future isolation is a consequence of void expansion and cosmic acceleration. It is not a threat in the traditional sense, but it represents a fundamental change in the cosmic environment. The universe is becoming emptier and more isolated. Structure is being eroded on the larger scales. The cosmic web is being pulled apart strand by strand as expansion overcomes the gravitational forces that created structure in the first place. For any advanced civilizations hoping to explore the universe, void expansion presents a barrier. The regions of space that are becoming voids are increasingly difficult to cross. The distances are growing, and the expansion makes travel across voids effectively impossible. The Milky Way's position within a filament is advantageous for now. We have access to nearby galaxies and galaxy groups, but this advantage is temporary. Over cosmic time, the expansion of voids will isolate all structures, turning the universe into a collection of disconnected island universes. The threat from void expansion is slow and inevitable. It operates on timescales of tens to hundreds of billions of years. But it is relentless. The expansion continues, driven by dark energy, pulling the universe apart, emptying the voids, and isolating the remaining structures. This is part of the long-term fate of the universe, a gradual dissipation of structure and connection. The cosmic web, so beautifully organized today, will eventually dissolve, leaving only isolated remnants floating in an ever-expanding void. The invisible architecture of the Milky Way cannot be seen directly, but astronomers have developed ingenious methods to observe and map these hidden structures. Each technique reveals a different aspect of the galaxy's invisible framework. Dark matter is detected through its gravitational effects. By measuring the rotation curve of the galaxy, the speed of stars and gas as a function of distance from the center, astronomers can infer the distribution of dark matter. If only visible matter were present, the rotation curve would decline at large distances. Instead, it remains flat, indicating the presence of an extended dark matter halo providing additional gravity. Gravitational lensing is another method for detecting dark matter. When light from a distant galaxy passes through a concentration of dark matter, the light is bent by the dark matter's gravity. This bending can be measured, revealing the distribution of dark matter along the line of sight. The magnetic field of the galaxy is mapped using polarized light. Dust grains in the interstellar medium align with the magnetic field, and this alignment affects the polarization of starlight passing through the dust. By measuring the polarization of light from many stars, astronomers can construct maps of the magnetic field. Radio observations of pulsars also provide information about the magnetic field, as the radio signals are affected by the field as they travel through space. Spiral density waves are observed through the distribution of young stars and star-forming regions. These features concentrate in the spiral arms, tracing the density waves. Observations at infrared and radio wavelengths can penetrate the dust that obscures the galactic plane, revealing the spiral structure more clearly. Molecular gas surveys map the dense clouds where stars are forming, outlining the arms. The galactic fountain and corona are observed in X-rays and ultraviolet light. Telescopes sensitive to these wavelengths can detect the hot gas in the halo, mapping its temperature and density. Absorption line spectroscopy provides detailed information about the corona. Light from distant quasars passes through the Milky Way's halo, and the hot gas absorbs specific wavelengths. By analysing these absorption lines, astronomers can study the properties of the gas. Tidal streams are detected by finding stars with unusual positions and velocities. Large surveys of stellar motions, such as the Gaia mission, have revealed many streams by mapping the positions and velocities of millions of stars. Computer algorithms search for overdensities of stars moving together, identifying streams and tracing their paths across the sky. Chemical composition measurements help confirm that these stars originated in the same satellite galaxy. Cosmic rays are detected both in space and on the ground. Space-based detectors measure cosmic rays directly, determining their energies and compositions. Ground-based detectors observe the particle showers created when cosmic rays collide with the atmosphere. Gamma-ray observations reveal where cosmic rays interact with gas, producing high-energy photons. Maps of gamma-ray emission trace the distribution of cosmic rays and the gas they illuminate. The warp of the galactic disk is mapped using observations of neutral hydrogen gas. Radio telescopes detect the emission from hydrogen atoms, measuring both their positions and velocities. By constructing a three-dimensional map of the hydrogen distribution, astronomers can see how the disk bends and twists at large distances. Stars in the outer disk also trace the warp, though they are harder to observe. The supermassive black hole at the galactic center is studied by tracking the orbits of nearby stars. These stars move so fast and approach so close that relativistic effects become important. By measuring tiny shifts in the stars' positions and velocities, astronomers can test general relativity and measure the black hole's mass and spin. Radio observations of Sagittarius A star itself provide direct images of the region near the event horizon. Each observational technique provides a piece of the puzzle. By combining data from different wavelengths and different methods, astronomers build a comprehensive picture of the Milky Way's invisible architecture. New technologies continue to improve our view. Larger telescopes, more sensitive detectors, and more powerful computers allow ever more detailed observations and simulations. Future missions will map the galaxy with unprecedented precision. The Gaia mission has already revolutionized our understanding of stellar motions. Future surveys will extend this work, mapping fainter and more distant stars. Gravitational wave detectors may eventually detect the mergers of black holes and neutron stars within the Milky Way, revealing compact objects that are otherwise invisible. Neutrino observatories could detect neutrinos from supernovae and other energetic events, providing a new window on the galaxy's most violent processes. The invisible architecture of the Milky Way is slowly being revealed. With each new observation, we gain a deeper understanding of the forces and structures that shape our galaxy. The Milky Way's magnetic field, threading through the galactic disk and extending into the halo, is not static. It evolves over time, and under certain conditions it could undergo reversals or instabilities that would affect the entire galaxy. Magnetic field reversals are well-known phenomena in astrophysics. On Earth, the magnetic field has reversed many times over geological history. The north and south magnetic poles swap positions, with the field weakening during the transition before re-establishing in the opposite polarity. The Sun's magnetic field also reverses approximately every 11 years as part of the solar activity cycle. During the reversal, the Sun's magnetic field becomes complex and tangled, leading to increased sunspot activity and solar flares. Galactic magnetic fields can also reverse, though the process is more complex and operates on much longer timescales. The mechanism driving galactic field reversals is thought to be related to the dynamo process that generates the field in the first place. The galactic dynamo is powered by the differential rotation of the galaxy and by turbulence in the interstellar medium. These processes stretch and amplify magnetic field lines, generating the large-scale field we observe. But the dynamo is not perfectly stable. Variations in rotation, changes in the gas content, or sudden energy inputs from supernovae can disrupt the dynamo. This could cause the magnetic field to weaken, become chaotic, or even reverse. During a galactic magnetic field reversal, the field strength would decrease significantly. The organized large-scale field would break down into smaller, more chaotic structures. The protection the field provides against cosmic rays would be reduced. Cosmic rays, normally guided and partially confined by the galactic magnetic field, would be able to penetrate more deeply into the galaxy. The cosmic ray flux in the galactic disk could increase significantly during a field reversal. This increased cosmic ray flux would have several effects. The ionization rate of the interstellar medium would increase, affecting the chemistry of molecular clouds and the process of star formation. For any life in the galaxy, a field reversal could increase radiation exposure. planets without strong intrinsic magnetic fields would be more vulnerable to cosmic rays during the reversal period. The duration of a galactic field reversal is uncertain. Based on dynamo theory and observations of field reversals in other contexts, a reversal could last anywhere from millions to tens of millions of years. Evidence for past galactic field reversals might exist in the fossil record of stars or in the structure of the interstellar medium. But detecting such evidence is challenging because the timescales are so long and the signals are subtle. Observations of other galaxies suggest that field reversals may be common. Some galaxies show magnetic fields with complex structures that could be interpreted as being in a reverse state or undergoing a reversal. Beyond reversals, the galactic magnetic field could also experience instabilities. Magnetic instabilities occur when the field configuration becomes energetically unfavourable, leading to rapid reorganization of the field. Magnetic reconnection events, where field lines break and reconnect in new configurations, could release large amounts of energy. In the galaxy, such events could heat gas, accelerate particles, and create transient high-energy phenomena. On Earth and the Sun, magnetic reconnection is associated with flares and explosive energy releases. In the galaxy, reconnection events could occur in regions where the field is particularly stressed or tangled. The galactic center, where the magnetic field is strong and complex, may be particularly prone to reconnection events. The interaction between the field and the supermassive black hole's environment could create conditions for large-scale magnetic instabilities. Parker instabilities, named after astrophysicist Eugene Parker, are another type of magnetic instability that can occur in galaxies. These instabilities arise when magnetic pressure and gas pressure are not in equilibrium, causing the magnetic field to become buoyant and rise out of the galactic disk. Parker instabilities could create large magnetic loops that extend into the galactic halo, similar to solar prominences but on a galactic scale. These loops could affect the structure of the halo and the flow of gas between the disk and halo. The threat from magnetic field reversals and instabilities is difficult to quantify. These processes have likely occurred many times in the Milky Way's history without catastrophic consequences, but they represent a potential source of variability in the galactic environment. Changes in the magnetic field could affect star formation rates, cosmic ray fluxes, and the structure of the interstellar medium. Over long timescales, field evolution shapes the galaxy's overall properties. For civilizations dependent on stable cosmic ray environments or predictable magnetic field structures, field reversals and instabilities could pose challenges. Navigation, radiation shielding, and communication systems could all be affected by significant changes in the galactic magnetic field. The galactic magnetic field is an integral part of the galaxy's invisible architecture. It shapes the flow of gas, confines cosmic rays, and influences star formation. Its evolution over time is part of the galaxy's ongoing dynamical story. Like the stars, the gas, and the dark matter, the magnetic field is not eternal and unchanging. It evolves, fluctuates, and occasionally undergoes dramatic reorganizations. These magnetic threats are subtle compared to galaxy collisions or supernovae, but they are part of the complex web of processes that determine the Milky Way's fate. The invisible architecture of the Milky Way is not unique. It reflects universal processes that operate in galaxies throughout the universe. By studying the Milky Way, we gain insights into how galaxies in general form and evolve. Dark matter halos are a fundamental feature of all galaxies. Observations of galaxies at all distances and all types show the same signature. Rotation curves that remain flat at large distances, indicating the presence of dark matter. Computer simulations of galaxy formation include dark matter as an essential ingredient. Without dark matter, the simulations fail to reproduce the observed properties of galaxies. The dark matter provides the gravitational scaffolding on which galaxies are built. Magnetic fields are found in virtually all spiral galaxies. Observations of polarized light and radio emission reveal fields with strengths and structures similar to the Milky Way's field. These fields are generated by dynamo processes, powered by the rotation and turbulence of the galactic disk. The universality of galactic magnetic fields suggests that dynamos are a natural consequence of disk formation. Spiral arms are a common feature of disk galaxies. About 60% of spiral galaxies show clear spiral structure. These arms are density waves, maintained by the self-gravity of the disk. The spiral patterns vary in strength and structure. Some galaxies have grand design spirals with 2 dominant arms. Others have flocculent spirals with many fragmentary arms. The Milky Way appears to be intermediate, with a few major arms and several minor spurs. Bars are also common. About 2/3 of spiral galaxies have bars, including the Milky Way. Bars play important roles in driving gas inflows, triggering star formation, and building central bulges. The presence or absence of a bar may depend on the galaxy's mass, rotation rate, and dark matter distribution. Bars can form and dissolve over cosmic time, so the fraction of barred galaxies may change as the universe ages. Galactic fountains operate in all star-forming galaxies. Supernovae and stellar winds inject energy into the interstellar medium, driving outflows. In low-mass galaxies, these outflows can be strong enough to expel gas from the galaxy entirely, shutting down star formation. In massive galaxies like the Milky Way, most of the gas remains bound and eventually falls back. The fountain recycles gas, enriching it with metals and regulating the star formation rate. Supermassive black holes are found at the centers of most large galaxies. The mass of the black hole correlates with the properties of the galaxy, suggesting that black holes and galaxies co-evolve. In the early universe, black holes may have grown rapidly, accreting gas and shining as quasars. Today, most supermassive black holes are quiescent, accreting slowly or not at all, as in the case of the Milky Way's black hole. Galaxy mergers are a universal process. Large galaxies are assembled from smaller ones through mergers over billions of years. The tidal streams and substructure we see in the Milky Way are evidence of this hierarchical assembly. In dense clusters of galaxies, mergers are frequent and ongoing. In the field where the Milky Way resides, mergers are less common but still important. The upcoming merger with Andromeda is a typical example of how galaxies grow. Warped disks are more common than once thought. Surveys of edge-on spiral galaxies show that the majority have warps in their outer disks. This suggests that warps are a natural consequence of galaxy evolution, perhaps driven by satellite interactions or misaligned accretion. Cosmic rays are produced in all star-forming galaxies. Supernovae accelerate particles to high energies, and these particles fill the interstellar medium, influencing gas dynamics and chemistry. In starburst galaxies, where star formation rates are very high, cosmic ray pressures can drive powerful galactic winds, ejecting gas and enriching the intergalactic medium with metals. The Milky Way is a typical spiral galaxy in many respects. Its mass, size, star formation rate, and structure are all within the normal range for disk galaxies in the local universe. This makes the Milky Way a valuable laboratory for studying galactic processes. What we learn here can be applied to other galaxies, helping us understand the universe as a whole. At the same time, every galaxy is unique. The Milky Way's specific history of mergers, its particular environment, and the details of its structure are individual to it. By comparing the Milky Way to other galaxies, astronomers can identify which features are universal and which are peculiar to individual systems. This comparison enriches our understanding of galaxy formation and evolution. The invisible architecture of the Milky Way connects us to the larger cosmos. The dark matter that fills our galaxy is the same dark matter that fills the universe. The magnetic fields that thread our galaxy are powered by the same dynamo processes that operate in galaxies billions of light years away. The cosmic rays streaming through our galaxy were accelerated by processes identical to those in distant galaxies. The spiral arms in our sky are density waves, just like those in countless other galaxies across the universe. Studying the Milky Way allows us to study the universe. Our galaxy is our home, but it is also a window into the cosmos, revealing the fundamental processes that shape all galaxies. As we conclude our journey through the invisible architecture of the Milky Way, we find ourselves humbled by the complexity and beauty of the structures that govern our galaxy. The dark matter halo, vast and invisible, wraps our galaxy in a gravitational embrace, providing the foundation upon which everything else is built. Without it, the Milky Way would not exist. The magnetic fields thread through the galaxy, guiding cosmic rays, shaping gas flows and connecting distant regions. These fields are weak but pervasive, their influence subtle but profound. The spiral density waves organize the disk, compressing gas, triggering star formation, and creating the beautiful spiral pattern we associate with galaxies like ours. These waves are not structures of matter, but patterns in space, ephemeral yet persistent. The gravitational potential wells, from the deepest at the galactic center to the shallow wells of star clusters, create a landscape of forces that guide every motion, every orbit, every fall of gas from the halo to the disk. The dark matter streams and substructure are fossils of the galaxy's assembly, remnants of the countless smaller systems that merged to form the Milky Way over billions of years. They remind us that our galaxy has a history, a story of growth and change. The galactic fountain cycles gas between disk and halo, regulating star formation and distributing the products of stellar evolution throughout the galaxy. This cycling connects the past and future, ensuring that each generation of stars enriches the next. The bar drives gas inward, feeding the central regions and shaping the inner galaxy. Its rotation creates resonances that organize stellar orbits into families, adding order to the apparent chaos of billions of stars. The galactic corona, hot and diffuse, fills the halo with gas that will eventually fuel future star formation. This reservoir is vast and largely invisible, but it holds the future of the galaxy. The tidal streams from disrupted satellites are visible reminders of invisible processes. They trace the paths of infalling dark matter and reveal the history of the galaxy's growth through mergers. The supermassive black hole at the galactic center, though small compared to the galaxy, dominates the central regions with its intense gravity. Its sphere of influence is a laboratory for extreme physics, where general relativity and strong gravity shape the fabric of space-time. The vertical structure of the disk, with its thin and thick components, records the dynamical history of the galaxy. Each population of stars tells a story of when and how it formed, of the conditions in the early galaxy, of the perturbations and interactions that shaped its evolution. Cosmic rays fill the galaxy, invisible but energetic, influencing the interstellar medium and coupling gas to magnetic fields. They are messengers from the most violent events in the galaxy, carrying energy and information across vast distances. The warp in the outer disk reveals the galaxy's response to its environment, to the tugs of satellites and the torques of misaligned structures. It shows that even on the larger scales, galaxies are dynamic and responsive. The influence of the local group extends beyond the Milky Way, connecting our galaxy to its neighbours and embedding it in the larger cosmic web. We are part of a community of galaxies, all moving together through space, all influencing each other. All of these structures, all of this invisible architecture, work together to make the Milky Way what it is. They control the motion of every star, the flow of every gas cloud, the birth of every new star. They are invisible to our eyes, but their effects are everywhere. Every spiral arm, every cluster of stars, every planet orbiting every star is shaped by this architecture, and we are part of it. Our solar system, our planet, our very existence is governed by the invisible forces and structures we've explored. We orbit within the gravitational potential of the galaxy, sheltered by the dark matter halo, bathed in cosmic rays, riding the slow oscillations of the galactic disk. The Milky Way is our home, but it's also a vast, complex and dynamic system. Its invisible architecture is a testament to the power of gravity, to the subtle influence of magnetic fields, to the profound effects of dark matter. As you rest tonight, under the unseen embrace of the galaxy's invisible architecture, remember that you are part of something much larger. You're a citizen of the Milky Way, a galaxy held together not by what we can see, but by what remains hidden. The stars above are only the visible part of a far grander structure. Beneath the light lies an intricate framework of forces and matter, a cosmic architecture that stretches across hundreds of thousands of light years, connecting us all. Thank you for joining us on this journey through the invisible architecture controlling the Milky Way. May your dreams be filled with the wonders of the cosmos, and may you rest well knowing you are cradled in the gravitational arms of our magnificent galaxy. Clear skies and peaceful dreams under the invisible architecture of the Milky Way.